Good evening, everybody. It's a pleasure to be here. Have you been the moon outside? Have you seen the moon outside? It's a gorgeous day. It's a good omen. It is my honor to be here today and introduce to you Dr. Alberto Rojo. I want first to thank you, Hope Culture and the Hendrix Murphy Foundation for doing so much for our programs in literature and language. This one included. I want also to thank you, chemistry professor, Dr. Caro, who contacted Alberto Rojo, and also wrote the proposal. And I'm thrilled to have Dr. Alberto Rojo here. Dr. Rojo is a scholar, he's an accomplished musician, he's a short story writer. He has a PhD from Biochemistry Institute in Argentina. He's a distinguished professor from Oakland University in Rochester, Michigan, and has published plenty on condensed matter. He's a specialist in quantum mechanics, and he's being a good promoter of science and literature, and in the intersection between these two fields, as well as art, music, painting, in the sense that this leap that the metaphor creates in the process of creation, be it art or be it science, are derived from one same attitude. And I have a quote here that I want to read. I translated it today, and I hope it's a good translation. It's an okay translation, at least. Dr. Rojo says about the confluence, right, between science and literature. This confluence is only possible when the imagination blurs the boundaries between disciplines such as science, philosophy, and art, and when thought and the search for truth are conceived as a single attitude. And that's what his last book that has inspired RTC courses are about. Finding these literary sources that have inspired scientific breakthroughs, and it goes all the way since the Iliad by Homer, going to the Renaissance, the Galilean invariants, and much more. Dr. Rojo is an inspiration to all of us, and he embodies the motto of the Hendrix College, unto the whole person. So please join me in welcoming Dr. Alberto Rojo.
Thank you very much. It's a real pleasure to be here. I can't imagine spending a better time since I came. Very hospitable, and making new friends and meeting some old friends. So this guy is Subrahmanyan Chandrasekhar. He's a Nobel laureate in physics for discoveries in black holes and formation of stars. And I happened to have met him in Chicago when I was a postdoc. And he was such a gigantic figure that it was intimidating in the corridors. And even in Thursdays at 4 p.m. we used to have a coffee and tea and cookies before the colloquium. And he would come to the room dressed in the same suit that he has here, and there was an oil painting of his behind. And so it was, the whole scene was so striking to me that I never dared to talk to him, mainly because he was such a prominent figure, and on the other hand, because I was working in different fields. Mostly, I was doing my postdoc, I was interested in specifics of my research. Later on, since I was an artist at the time, but I hadn't explored yet the intersections that I later explored, I discovered that he has a line in one of his books, a book that's called Truth and Beauty. And you could read the line, but I'll read it for you. An incredible fact is that which the human mind perceives as beautiful find its realization in the external world. So, to me, that's one of the most important lines that have been written in connection with art and science. To me, what this is saying, what he is trying to emphasize, is that the laws of physics, our description of nature, is a creation of the mind. To talk about the laws of physics as governing the universe is more of a religious idea, I claim. The laws of physics are drawings, pictures, poems that describe the regularities of nature in a unified way. And they express and are informed by our senses. As the same creative act that generates the laws of physics, the same imagination that creates science is the one that creates art. I have a theme for a short story that you might want to write, and it's the idea that we make connection. I never wrote it, but I always mention it, and then with the hope that someone's going to send me the short story later. We make contact with a civilization that's remote and that it's evolved to generate intelligence. But since the evolution it's a random process, it's practically for sure that the brain is going to be different. That the knowledge that they create is going to be different because they have different senses. Right? We are essentially visual and we hear, but it's our way of perceiving light that informs light and other natural phenomena. It informs our creation of metaphors. So there is not only one science, that's what I'm trying to say. There's a personal taste in science. You might have read about this story that it's widely mentioned that if, say, Beethoven hadn't existed, the Fifth Symphony would not exist. Or if Vermeer didn't live, we wouldn't have the girl with the pearl earring. But if Einstein didn't exist, or wouldn't have lived, we will have the theory of relativity and we will have the laws of Newton. That is not completely true, I claim. If you look at the development of the physical laws, they are a reflection of the personal taste of the scientist. Many examples, I'm going to tell you only one of them. When Einstein develops his theory of relativity, he talks about curvature, and he generates a new vision of mechanics in terms of curvature space. And then later Feynman says, I could do it completely different. I could start with a completely different picture and arrive at the same description. So there's not a unique set of laws that describe the same nature. And so I want to substantiate that notions with some stories, my favorite stories that speak about that intersection and how the notions of art gravitate in the development of physical theories, and vice versa. So the universe doesn't organize itself as universities. One of the things that I like to talk about is the role of metaphor as an instrument of discovery, just like the telescope and the microscope, right? Exploring the limits of language. That's what, to me, poetry is, after all. We have a finite number of words, a finite number of combinations, but the universe of the possible descriptions is infinite. So it's a discretization of our description of nature that language proposes. And in those interstices of this discretization is where the inexpressible lives. And to penetrate that, to attempt to express the inexpressible, is where we need the poets. And you will see that if you look closely, you will find metaphors in all the descriptions of physical problems. He is one of my favorites. It's the tree of life, right? By Darwin. This is a picture of Darwin's diary where he draws a tree, right? The development of life is not, there's no tree there. There's plants, right? But the what he's talking about is the branching of the species, right? As though there was a tree. So the tree is a metaphor there that's very helpful for him to develop the final theory. There are many more. One of my favorites in 20th century physics is the arrow of time. That comes from Eddington. Time is perception, but to talk about an arrow that goes in one direction from past to future is already a metaphor. This is another guy that has explored these connections implicitly, the connection between art and physics, between poetry and science. This is Galileo, and he is the generator, the creator of what we call physics today, in the modern sense, the interaction of observation with theory, experiment with theory. His most famous experiment is the free fall of bodies, right? And he said, well, if I have this object is at rest with respect to the table, or with respect to the floor. If I release it, it's going to start moving. So it's going to go from rest to motion. In other words, it's accelerating, right? But how is it accelerating? There are many ways of acceleration. And Galileo says it's going to accelerate uniformly. Why? Because nature, in all its works, quote, looks for the simplest, easiest, and fastest means, end quote. Why would nature find for the simplest way? We don't know. And so he tries to explore that quantitatively now. That's his contribution. So he has to say, okay, so how do I measure the free fall? So I have to measure distances and times. And to measure distances and times, I need precise clocks. And there were not, in the 1609, there were no clocks that would measure time with precisions of milliseconds or tenths of a second. So how do you do that? How do you measure, how do you check if acceleration is constant? And Galileo happens to be a musician. His father was a full-fledged musician. He was a musician himself. So I think the start of physics, the beginning of what we call physics today, is a musical event. Because he resorts to a musical concept to figure out the acceleration. So think of an inclined plane, which is basically the same rate at which, the same law of acceleration applies to a vertical fall or an inclined plane, except that the acceleration is going to be smaller, but the law is going to be the same. So suppose you have an inclined plane, and you put little bells on the inclined plane. And the particle rings the bell every time it hits the bell. So in the first second, or the first interval, ding, ding, and then this third one, the particle is faster than the first one, right? Because it's accelerating. So you will hear ding, 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 right? And so he says, okay, I cannot tell the precise time of those intervals, but we humans have a good sense of rhythm. That's why we can dance. And I could say, you can't tell if that is 1.1 second, 0.95 seconds, but you can tell that there are equal intervals if you have a sense of rhythm. So then what he does is he spaces the bells so that rather than listening to ding, 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 you can ding, 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 equally spaced in time. So the question is, how are they spaced in space when they're equally spaced in time? So he finds, and he says it's in that way, they are separated according to the odd integers. So the first one is 1, the second is 3, the third is 5, 7, etc. Okay? That's the experiment. So let me represent the distance by a square, right? So in the first second, it travels 1 square. In the second second, it travels 3 squares. In the third second, it travels 5 squares. The distances get longer, etc. So the distance goes as the square of the time. And that's uniform acceleration. So a law of physics that starts our understanding of the regularities of nature as a musical event. And Galileo was a scientific artist, I claim, because in his discoveries, we see how the knowledge of art can inform your scientific development. It's very eloquent. This is one case. The other case is his use of metaphor. As a poet, he uses the metaphor of the universe as a book. It's a metaphor that existed in medieval times, and before Galileo, there were two main books, right? The Bible and the universe. In order to read the Bible, you have to be a studious cleric, and no one can read the universe. But Galileo says, the book of the universe, a book, right? It's a book, can be read because its characters are written in mathematical language and are triangles, squares, and other geometric figures. And without them, you can't understand a thing, and you wander in a dark labyrinth. That's his line. And no wonder Italo Calvino says that Galileo is the best writer in prose in Italian. The best writer, because I mean, if you include every writer, you have to include Dante, and Dante is not probably better, right? But and his interests were broad in Renaissance, and he was also interested in painting, and he has taken classes in perspective. And this is the image of the Virgin Mary as it was depicted in the early Renaissance. It's the Virgin is standing on a spherical moon, perfectly spherical. It's the symbol of purity, and that's the Immaculate Conception. And it's a transparent, perfect sphere, very important in Catholic tradition. And the non-white parts of the moon are imperfections that are of the transparency, but not of the sphericity. That was the theory. In 1609, Thomas Harriot, the astronomer in London, in England, looks at the moon for the first time. That's June 1609. And he describes the boundary between the illuminated part and the dark part as rugged. But he doesn't make much of that because he attributes that ruggedness to the imperfections of the lens. Now, Galileo looks at that, and he had taken perspective, and he knew himself how to paint. So he paints these watercolors with very clear parts on the dark region and some dark spots on the clear region. And from the width of those dark and clear parts, he says, oh, these are craters. And I can estimate the height of those craters by my knowledge of perspective. So, a discovery, an important discovery, not as important in astronomy, but to the interaction with religion, because now the moon is not perfectly spherical, the moon has craters. And that was a time where Galileo, this is November 9, 1609, when Galileo was getting along with the church. He was a great theologist, great philosopher, and a great believer in God, but he got in trouble with some structures of power. At that time, he was getting along very well. And Cigoli, a friend of his, a painter, was commissioned to paint the Immaculate Conception, Santa Maria Maggiore, and he painted it with the moon with craters. Last time I went, I couldn't, it was covered, I was restoring it, so there was a mesh that I couldn't see take a picture of the moon, but you could glance at it, and you can see that the moon has craters. It's not the Immaculate Conception now, it's the Assumption of the Virgin, but still. So here we have Galileo contributing to science with knowledges of music and painting. And much as Galileo was the great writer in prose, then we have the great writer in the great poet from Italy, Dante, who has a lot of anticipations. Also another element to me that's very important in the intersection between arts and science, the anticipation of ideas that appear in works of fiction. To me, the most important one is this one, and that appears in Paradisos in Canto 28. So this is the paradise, right? And the paradise has this very clear geometric structure that has been studied before, but not describes as much precision as Dante describes it in the Divine Comedy. So you have the Earth, and then you have the planets. And then you reach a point where you can see the edge of the universe, right? The edge of the universe. It's called the primum mobile. If you Google primum mobile, you probably get a phone plan. But here it's the edge of the universe. You know? And then, to some people, there's nothing beyond that because it's the edge of the universe. But if you keep going, you see there's a celestial. There are the angels and there's the out of the world structure. But the important thing is that you go from the center, from the Earth, you cross the spheres, and then you keep going. They keep going, and the spheres contract. So you're always going out. The spheres first expand and then contract. So Mark Peterson wrote a book, and first an American Journal of Physics, claiming, and I'm with him, that that's an anticipation of square space. Centuries before Einstein. Because if you think of a sphere in 2 dimensions, the spherical surface of the Earth, say, that lives in 3 dimensions, but it's a 2-dimensional surface. You go from the North Pole, you start crossing the parallels, right? You go towards the south, you cross the parallels, you get to the equator, you keep going, and the parallels shrink. That's only possible because the surface is curved. Now, if the 3-dimensional space is curved, that could also happen. Because you could it's difficult to think of a 3-dimensional space living inside of a 4th-dimensional space, but mathematically it's possible, and you get exactly this. So an anticipation in medieval times of the curvature of space by studying with obscene detail the structure of Dante's Inferno, well, in this case, the Paradiso. So I collect these examples where, on the one hand, science can be anticipated in literary works, and perhaps philosophically more important, cases where the idea of art, the ideas of art, the subjectives, the so-called subjective notions, inform the development of physical theory. So I will show you some examples of literary anticipations, one more, and then cases where the subjective notions, the idea of symmetry, elegance, and beauty, is the notion that informs the development of a physical theory rather than the explanation of an experiment that was not explained. So this is another very interesting example of scientific discovery anticipated in literature. To me, it's still a mystery how this happened. So this is Jonathan Swift, Gulliver's Travels. There's, Gulliver travels to many places, and there's an island called Laputa, where the astronomers are very advanced, much more advanced than the astronomers on the Earth. And they have telescopes that are very powerful, right? And they had found, this is 1726, that Mars has 2 satellites. And he even describes in the text, I'm not going to read it, I'm going to probably read it for you, but he describes the orbits, the size of the orbits, the periods of the orbits. He says that the square of the period is the cube of the distance. So he writes in a piece of literature in 1726, Kepler's laws, and predicts that Mars has 2 planets, and predicts the periods and predicts the distances to Mars, and they're pretty close. And they were discovered in 1877, right? Still a mystery how he got that, but I think that what might have happened is that he said, okay, Mercury doesn't have one, Venus doesn't have one, the Earth has one, Mars, I don't know, Jupiter has 4, because Galileo had discovered 4. Okay, so 0, 1, something, 4, 2. That probably. And now he says, what's the distance? Okay, so it has to be close. Because if it's far, the telescopes would have seen them. That's what happens with Jupiter. What Galileo saw was the Jupiter here and points that they moved. Right? And Mars, if you focus your telescope, 1600s or 1700s, you can see a moon. So it has to be close. So it's a coincidence, because now he said 0, 1, 2, 4, but now it's 0, 1, 2, 75. Because at least it depends how you count, but Jupiter has tons of moons, right? Coincidence. But I think it's a beautiful coincidence, because it's a paragraph that is, in itself is very nice, and has a scientific prediction. A notion that, as I say, is crucial for the intersection between the idea of beauty and truth. The search for scientific truth is symmetry. You know, symmetry, what is symmetry? Okay, symmetry is an operation, from a math point of view, say, is an operation that would leave an object unchanged. Right? So if I have a cube and I rotate it 90 degrees, and if I show you the cube and then you turn around and I rotate the cube and I look it back, I can't tell if it's the original cube or the rotated cube. So that's a symmetry of the cube. And the sphere has infinite symmetries. The triangle I can rotate it by 60 degrees and 120 degrees, and they have the same triangles, it's equilateral. Mirror symmetry. This is not perfectly symmetric, Michelangelo, but there's some symmetry there, because it's almost a mirror image, right? So symmetry was an idea that's associated with beauty. Faces that are more symmetric tend to be more attractive. But then here comes Emmy Noether is a physicist that establishes a very important connection between symmetry and something called conservation of something. So every time there's a symmetry in a law of physics, for example, the cube has a symmetry, something has to be conserved. Okay? And she starts looking at this because in relativity, in general relativity, the idea of energy was not clear how to compute. You know, energy is something that no one understands exactly what it is, but we know what it is, right? We have many ways of computing the energy of something. Now, and it happens that energy is a quantity that's constant in the universe. It's always constant. Energy is conserved. That's a law of physics. Right? There are different forms of energy: chemical energy, gravitational energy, potential energy, kinetic energy. But in any process, the energy is never altered. So when you talk about an energy crisis, that's not true. It's entropy crisis. It's energy in certain forms that we're in the need for. And the fact that the laws of physics imply conservation of energy is because there is a symmetry in time. So the universe is the same today as it was yesterday in terms of its laws. If the laws of physics don't change with time, then there is something that is conserved, and that is energy. And those kind of notions are attributed to this woman called Emmy Noether. And I remember studying that theorem and finding out that she was a woman very later on in my career. So as an example, let me give you an example. So suppose you have free space, okay, and you have a tennis ball that's moving. And if there is no force on that tennis ball in free space, there's nothing else, it will keep moving at constant speed. if there are no forces. That's Newton's law. In order to change its speed, we have to act with a hammer, say, and change its velocity. And that has to act at a certain position. So as long as there's no force that acts on a certain position, the velocity is constant. So if there is symmetry of translation, in other words, every point is the same because there's no hammer anywhere, velocity is conserved. Okay? That's a symmetry. And the conservation associated with that symmetry. So we go from mechanics to electricity. Now, this is a kind of a pornographic slide that you don't have to follow it. Think of it as going to the British Museum and seeing the Rosetta Stone. It's beautiful. We don't know what it means, but it's beautiful, right? So, what is this? These are called the equations of electricity and magnetism, and describe something called the electric field. It has a name, a German name, because it's a German name. Gauss formulated the first equation, right? That talks about electricity and charges. Then there's a law that says that the magnetic field, it's always closed. The lines of field, if you think of a magnet, you've seen these field lines, they're always closed. Then there's a British guy, Faraday, has another law of electricity. And then there's Ampere, all the nationalities there, the Argentinians. You have an Ampere that, so these four laws existed in the 1800s describing electricity on the one hand and magnetism on the other side. But Maxwell was looking at these equations and says, there's a problem here. There's a symmetry lacking. Because, I'm just going to say the words, charge is not conserved. Charge can be destroyed in these equations. So we have to add a term. He was on vacation in Scotland, and he was playing with the equation. Says, I have to add a term to restore the symmetry. There was no experiment that he wanted to explain, right? And so you had electricity, the light rays, and you have magnetism, the compasses, right? Interacting a little bit with each other, but nothing else. And he says, well, I'm going to add a term. And he puts a term to restore the symmetry of the equations. And all of a sudden, these equations admit a solution that didn't exist before. You can get waves with that term. Something completely unexpected. And says, what are these waves? Electricity and magnetism, he says. So I'm going to use these constants that I got from electricity. I'm going to use this number that I got from magnetism. I'm going to compute the velocity of that wave. But he didn't have the numbers because he was on vacation. So he went back and put the numbers and, oh, this is the speed of light. Wow. And so there was light. And so he proved by, the message here to me is that by trying to restore the symmetry, which is a notion that in principle we could say is subjective. Why would God make the laws of physics symmetric? Or why would it make them according to what we perceive as symmetric, which is a pleasant sensation, after all? So from Maxwell, that uses symmetry to figure out light, comes Einstein that says, there's still something that's not completely symmetric. And this is the first line on his paper, and I'm going to read it because the font is kind of small. It is well known that Maxwell's electrodynamics, as usually understood at present, this is the first paragraph, when applied to moving bodies, leads to asymmetries that do not seem to attach to the phenomenon. He's uncomfortable with the symmetries that even though Maxwell has symmetrized them in some way, there is still some symmetry that is unpleasant. And the asymmetry that's unpleasant is probably simpler to explain. And that's in the second paragraph. And he says, suppose I have a loop of wire, okay, just a coil, and the magnet. And I move the loop. So it happens that the Maxwell's equations predict a current in the loop. Now, the loop is at rest, and I move the magnet. There's also a current, according to Maxwell. But different equations. for the same current. That's strange. How come you get the same result and you get different equations? Why different equations? Because there is a medium. And in one case, the magnet moves with respect to the medium, and in the other case, the coil moves with respect to the medium. But Einstein says, if the equations are the same, there shouldn't be a medium. And that's the revolution. Because now the electricity and magnetism can propagate in vacuum. There's no ether, there's no medium, and that has enormous consequences in our description of space and time. But I want to emphasize that Einstein starts his line with poem, basically. I don't like the symmetry of Maxwell's equations. This is Paul Dirac, crucial figure in the development of quantum mechanics in the 20th century. Again, another case of unification. The history of physics is, to a large extent, the reconciliation of ideas that are irreconcilable at first. For example, Galileo is responsible for the first unification, the unification of motion with being at rest. So if there's no force on a particle, the particle keeps moving on a straight line, right? Or stays at rest. Right? Before Newton and Galileo, the force was the cause of the motion. For Newton, the force is the cause of the change in the motion. So if there's no force, it will not change the motion, so it will either move at constant speed or stay at rest. So being at rest or being in motion are the same thing, seen from different perspectives. So it's relativity at the Galilean level. And then Einstein unifies that for electricity, and then Dirac tries to reconcile two ideas that were developed in 1927, quantum physics on the one hand, and relativity on the other hand. And how does he do it? Playing with the equation and trying to find the simplest way. And he was asked when he was in Moscow, what's the most important element that a physical theory should have? And he replies, the laws of physics must have mathematical beauty. So if they're beautiful, they're going to be true. And this is a paper in which he, and if you look at the abstract, the abstract says, mathematical beauty is important in particle theories, two of which are described here. And he goes on to describe how he finds the equation, the simplest equation he could find, and he gets to the antiparticles and a lot of new phenomena that emerge from looking at the most beautiful and simple description. So this is the time where quantum physics starts being a main character in physics, and you might have heard the iconography of quantum mechanics, and one of the key elements is that particles at the microscopic level can be simultaneously in many places, for example. A notion that doesn't have any counterpart in our everyday experience. Or a particle could be simultaneously wave and particle as we understand it in everyday life. So there are no words for that. We don't have words for that. And that's why Niels Bohr says when it comes to atoms, the language can be used only as poetry. The poet, too, is not necessarily so concerned with describing facts as with creating images and establishing mental connections. So the 20th century, and even before, is a century with science getting at a loss of words, right? So that's where we need the poets. We don't have a concept expressible in the same words that we use to describe a muffin or a tennis ball, to describe these entities that live in the microscopic world. Or we don't have words for, or ideas for a moment like the Big Bang postulates that doesn't have a prior moment. Right? We're used to moments that have a prior moment, but if there's a beginning, what was before that? We don't know. We see the mathematics, but we don't have words for that. And I think that Heisenberg summarized that idea in a very, very poetic way, in a poetic, in a physicist kind of way, if you want. But I think we wish to speak in some way about the structure of atoms and not about the facts. But we cannot speak about the atoms in ordinary language. So what he's saying is that language has its limitations. And some physical concepts make that very evident. And poetry is the territory of the ideas that cannot be expressed, attempts to express the inexpressible. The idea of wave-particle duality, of particles behaving as waves, starts with de Broglie. Quantum physics had been developed for many years, from 1901 to 1925, with trying to tinker with the classical physics equations, making the minimal modifications so that we'll account for the experiment. But the equations were not perfectly consistent until de Broglie proposes the idea of wave-particle duality. In other words, an electron, subatomic particle, can behave as a wave. And in his, why am I showing you this? Because it's to me one of the intersections of science with music, because you have the waves. And de Broglie was a musician. And when he talks about the waves, and the waves that describe certain energies or certain orbits of the atom, of the electron orbiting around the nucleus, are the waves that are in phase harmony. So it's like a tuning condition. So he uses the musical metaphors to advance in his description of the allowed frequencies, the allowed energies of a subatomic particle that behaves simultaneously as a particle, as a wave. To finish, I'm going to show you some examples that express my interest on a second interest in the intersection of arts and sciences. I sort of have two sort of rivers that I explore in the search for unity. One is the philosophical epistemology of it. So how is it that there are aesthetics elements in science and a lot of rigor in the arts, and that they don't serve antagonistic divinities, right? So they're not opposed visions in the search for truth, but there's a common territory. That's on the one hand. On the other hand, I like to explore examples in the arts that are vehicles that facilitate the teaching of science. Right? And for example, if you think of the musical consonance, the idea of musical consonance. So what is music? Right? So you'll find definitions in many places. I think that the most concise definition of music, and that comes back to Galileo, is that music is rhythm. Okay. And so I have here a sort of depiction of a regular pattern that to me is kind of a metaphor of music, in the sense that I like to think of music as a crystal of time, or something that repeats in time. So you have a pattern here at the bottom that repeats one. The unit pattern in time is the one at the bottom. Then you have a second pattern that's twice as fast. Then you have a third pattern that's 3 times faster, 4, 5, etc. And if you represent that in a chord, you see that the first one is 1, the second one is an octave higher for those that know music, and then the other one is a fifth above the octave, etc. So that thing that we call a consonance, or the musical intervals that are pleasant to the ear, are patterns that agree with each other, that we can represent it as patterns that agree with each other. For example, this is an interval of a fifth. Right? I don't know if you're musicians, twinkle, twinkle, that's a fifth. Right? And a fifth are 2 notes that if we were to sing a note and a fifth, we will see that it sounds pleasant. The interval sounds pleasant. Consonant. It's a consonance. Why is it a consonance? Because it's an agreement between two patterns. And the patterns are 3 versus 2. So, 3 with 1. That's 3 against 2, right? Now, if I play 3 against 2, I get something like this. I don't know if you can hear that. You hear the rhythm, but now I'm going to play it faster and faster and faster. At a certain point, you're going to start hearing the interval. It's not. You're not going to buy a CD of this, but see that, the interval? And the speed is increasing, the frequency is increasing, the ratio between the two, microscopically, is 3 against 2, right? See, the time between this is decreasing. You have a consonant chord there, 2 notes. That corresponds to the agreement of patterns of 2 against 3. I love this piece. And then it comes down. You hear a lower frequency until you start discerning the microscopic structure. And you lose the idea of tone, and you can discern individual. But you'll see, it comes back. Okay? There's another one that I could play, but it's because I like the album. But this is a complicated one. It's a 10th of a chord that has 4, 5, and 6. That's also a consonant chord. First you hear the individual beats that don't make much sense, but it's a rhythm, right? Which with many intermediate ones, and then there's a pattern where they all coincide. That defines the common note. And when it goes higher, of course, it's kind of it's not a musical instrument, but you can hear the chord that results from the agreement between patterns. Different chord now. Okay? Consonant chord. That has. So it's basically a triad and the first inversion for those who are musicians. Yeah? It's a chord. Okay, and then harmony is the agreement between patterns. When you shift from one pattern to the other, you have to go continuously, like in Escher's painting. Right? Because you're going to change one pattern, you have to find elements. So there's a deep mathematical connection in that respect, many more connections. So I'm going to, my last examples come from painting, and another example of using paintings for illustrating physical phenomena. In the case of optics, this is a Manet, a Folie Bergère, and that's Suzanne. This is the waitress, and there's a mirror behind, right? Now that painting has mistakes. Mistakes, there are no mistakes in art, but certain violations of the laws of reflection of mirrors, right? Can you spot some? So, for example, you can see that there's a table reflected, and the table is parallel to the other table, so it means that the mirror is flat, right, and is parallel to the table, right? Now, if the mirror is flat and parallel to the table, we shouldn't see her because we are the observers. She's on the right. And then the bottles are misplaced and the sizes are wrong. Because when you see something, and I invite you to do this experiment, you're in a foggy bathroom because you just took the shower, you look at yourself in the mirror and you trace your head with your finger. You will see that that is exactly the half of the size of your head, independent of the distance, because of the law of reflection. So when it's reflected, it's half the size. If you go further, your face is going to be smaller, the picture is going to be smaller, and you're going to fit there. So this is one of the classic examples. I'm going to show you. We're a mature audience. I gave this talk on YouTube once, and I was censored by the robot. This is my favorite painter and one of my favorite paintings. This Venus, right, with an angel reflected. So you can see that, as it happens in many paintings, the perspective is correct. The folds of the drapery are perfect. The anatomy is first. The chiaroscuro is fantastic, but the reflection is wrong. For some reasons that I don't understand, compositionally, it works to distort the reflections whenever you see the moon or something that's beyond our direct experience. There's an invitation to describe what's reflected as violations of the laws of reflection. What's the mistake? What are the mistakes? Mistakes in quotation marks. Well, if we are looking at Venus's face, that means that Venus is looking at us. And we're invited to think that she's looking at her reflection, right? So the angle of the mirror is wrong. But the size of the head is wrong. It's too big. Right. I did the experiment myself with clothes in my class, and I put the mirror exactly the same distance, and you can see the face is much, much smaller. Right? It wouldn't have worked as a portrait with that face, but that's a realistic description of the mirror. Here is one of the paintings that's the most important one in I would say, one of the great paintings in the history of painting, for many reasons, the execution, but mostly because here's Velázquez on the left, painting the king and the queen that are outside of the painting, that are looking at themselves in a mirror that is inside the painting. That has never happened before, right? So the question is this correct? Is the reflection correct? And I claim it is, because the size of the mirror has to be, if it fits two people, has to be the size of one person. And if you look at the guy that's behind, it's roughly the size of one person. The mirror is roughly the size of one person. Well, forgive Velázquez for this one. And if you make the vanishing point, it should coincide, this is a detail, with the eye of the king or the queen. It doesn't quite coincide, but it's better than the for some reason that it's still a mystery to me. Mirrors are invitations to transgressions of the law of reflection. But that doesn't mean that that these are mistakes. Quite the contrary. This is one of my favorite lines by George O'Keeffe, that nothing is less real than realism. Details are confusing. It is by elimination, by emphasis, that we get at the real meaning of things. And that's what Galileo did. Because if you think of a fall of an object, it doesn't fall like uniform acceleration. If I throw a piece of paper, it's going to fall like this. So you have to simplify by eliminate the air to get to the law of reflection. Every time you draw a picture, you have to eliminate something. If you do it through a theory, you have to eliminate something. So I hope that I have give you some useful examples on the intersection of art and physics that to me is summarized in John Keats' line that says, beauty is truth, truth is beauty. That is all we know on earth and all we need to know.
So on the basis of the painting where you're saying the face was incorrectly positioned, for the one that you recreated, do you think by chance that the artist was actually making it more of a meaning towards just kind of looking at the viewer themselves in the same way that she was probably looking at the person who was drawing her, or painting her, my apologies?
I think that, well, no one knows. There's a theory that he painted the face big because if he painted the face small, he would have to paint the reflection of a nude person. And I don't think that's the case. I think it's a compositional thing. He painted the face after the, he wasn't looking, because if you look at the reflection, if it's alive, definitely I'm sure he played with, he painted the model live, the angel as a kid as a model, but then the reflection he painted afterwards because he was trying to think of what would work better, and for some reason the mind wants the mirror to be the same size. I don't know if I'm answering the question, but I think that's what happened.
Okay.
Hi, thank you for that. That was wonderful. This might sound less like a question for an audience and more like professional advice, but is this something that plays in your teaching of physics, to talk about the inventive and imaginative ways to arrive at a truth from a direction that seems to be outside of the disciplinary context in which a student finds themselves? So I wonder, do you teach something like this to your physics students?
I try to, yes.
Okay.
Yes.
And do you?
These are most of the examples that I use in my class, and yeah.
Okay, and so you do it by showing examples.
Yes.
And okay, and how does
And
that?
then we practice things like drawings and.
Okay.
It's-
How does that work to your class?
It's mixed, but I get a third of the students that get the message, and I think that's enough.
Okay.
But,
Thank you.
But yeah, but sometimes I teach musicians and I take like my non-science major classes, and I have fun with groups of students that are mixed majors. And this is a unifying principle. Of course, students want to know the grade, if this is going to be the final, but I smuggle these ideas.
I
So
do
the
have
emphasis, the emphasis is that to create something new, the process is the same. If you're creating a piece of art or you're creating a paper.
I do have a question that I've kind of been thinking about, bringing it back to a point that I've thought about before in the past before this. But consciousness can be seen, it's a very abstract topic in general. Do you find there's a way to relate physics within consciousness? As I've seen, of course, there's such things as neurophysics, but it kind of does not anywhere touch the top of a consciousness being more theoretical. To you, with, of course, combining other degrees of consciousness, like artistical interpretations of things or metaphorical interpretations of things, do you feel like with the physical sciences, or specifically physics, can there be any relation there?
If the question is whether physics is going to give us the answer of consciousness, I'm skeptical that's only physics. And it's going to come from an intersection of artificial intelligence and psychology and neuroscience and physics, and we're still far from it, but it's perhaps the biggest scientific question, I think.
Thank you.
To formulate the question even is difficult. There's a question in the back.
Hi, first of all, thank you for doing this. I had a question about a concept that you talked about near the beginning of your presentation. You said the line, not all science is the same, and I thought that was just an incredibly interesting concept to think about. And that was in relation to like the creative writing prompt that you were giving us. But I was wondering if this exists outside of that prompt, and if you have any just like, I don't know, like off the dome like examples or concepts or theories about this, because I purely out of curiosity, because I'm just an English major, but I just thought that was a super cool concept.
The idea that there is a personal taste in physics, and I gave the example of relativity with Feynman and Einstein, but there are examples that work in that direction are theories that were wrong but worked. If you think, for example, the caloric. The caloric is a theory that says that heat is a fluid that goes from hot bodies to cold bodies. We don't accept that theory today. We accept that heat is just the motion of particles. But the caloric was the theory that Carnot, the thermodynamics, one of the creators of thermodynamics, used to explain his cycle from which the Industrial Revolution and the steam machines were developed. So the whole development of technology of the steam machine was based on the wrong idea that worked. So if something works, it doesn't necessarily mean that we are describing nature. That's what I'm going to say. If you think of there's a little machine there, and I did have it's on the arrangement that Tiffany prepared that describes the planetary motion. You can play around with it in the lobby, and that's it's the sun is at the center, and the moon is revolving around the Earth. That's in turn revolving around the sun. That's the heliocentric model. Before that, we had Ptolemaios describing the Earth as the center, and the planets orbiting around the Earth and the sun orbiting around the Earth, with a description that worked fantastically well. The model was wrong, but the prediction of the eclipses was correct. The retrograde motion of the planets was perfect. They had some mistakes, but it worked very well. So a wrong model that works well, right? And so those are some examples. There are many more in biology, and that says, okay, if there is a sociology and there is a creation of someone that comes with a model that works, and there could be another model that works. If that one is wrong and it works, there could be another wrong model like that. And even if there's a classic essay that I have to confess that I don't understand it 100%, but I understand some of it by Nobel. It's supposed to be the most influential philosophical article in the second half of the last century, is what's inside the mind of a bat. Okay? And he says, basically the idea is, I can imagine what would be to be very big. I can imagine myself being very small, but I can't imagine being a bat that creates a picture of the world based on sounds only, right? So my drawings of the world are with different senses. I cannot imagine that, right? So if a civilization has only sounds and the bats are the Einsteins, it's probably they're going to develop a technology that controls them in order to control nature with different physical laws. So I recommend that article, but it's difficult.
Not an English major, but a big fan of books and literature. I was wondering, what inspires you whenever you teach physics? Do you find yourself leaning towards a specific type of artist or writer or any of the sorts, or do you find yourself leaning towards like a time period whenever you teach a class?
Oh, that's a great question. No, I rotate them because I'm constantly studying art, so I have my favorite examples. Galileo is one of my favorites, and Velázquez is one of my favorite painters, and Bach, and Borges is a favorite writer. But I keep discovering new ones, and I can't wait for the moment to tell the students, if I develop the idea correctly, the connection. So I gravitate, if I had to choose a period, I gravitate to the Renaissance till the end of the 19th century, and terms of art and music. And Bach for
Understandable. Renaissance art is very beautiful. Thank you.
You're welcome. There's one in the back. I don't know if we have time.
Sorry, Dominic, for making you call this way. Thank you for this beautiful talk. And I was a little late, so forgive me if you covered it in the beginning. But I was just in time to hear all the praise for poetry and poet. And as a poet and professor of poetry, I was really into your presentation. And as you were talking, I was almost thinking of like lines of equation. I was also thinking of as lines of poetry to some extent. And you talked a lot about symmetry, beauty, and truth. And one thing for me in poetry is mystery. And mystery not as in a problem to be solved or a puzzle to be solved, but something to be lived, something just perhaps not unlike love to be felt and be consumed by it. So I was curious if there's been anything in physics where there's an effort not to explain or demystify mystery, but to embody and perhaps even deepen and make it more complex.
What a great question. My last line was from Keats, you know, and Keats is part of it's. Even though he says that, and I quote him, you might have heard the Unweaving the Rainbow poem, in which Keats is part of a movement of the disenchantment that science brings into the poetic world. So he accuses Newton of unweaving the rainbow, because now he has explained the refraction laws that give us the rainbow, so the rainbow is no longer magic. Right? Whereas I think it's quite the contrary. Right? Because understanding how the rainbow works, it's adding a new pixel to our appreciation of that mystery of existence. The beauty of the rainbow is reinforced by our knowledge that there's a trick of nature that we have solved, and that's the rainbow. And you used the word mystery, and I think that's key, because most of us scientists that are not believers in, let's say, a unified religion, we are bound to a mystery, and that's in the pure etymological word of religion, religare, to be bound to a mystery. Right? And what science does, in my view, and in the view that I've read from Einstein, Heisenberg, Newton, Darwin, it's the sense of awe, right? The sense of awe, and how science deepens that. You use the right words. I think it deepens that mystery. Perhaps it's implicit in your question that there is, in solving something, we are depriving it from the poetic aspect. I don't know if I got that, but I sort of sense that. But I think there's a permanent mystery, and I'd like to quote Paul when he says in the Corinthians that we only know in part, and when the eternal comes, that what we know in part would cease. Right? So we always know in part. There's always a mystery, and that science deepens and enriches that mystery. That would be my answer. I don't know if it's the answer, but I took two questions as an excuse to express my vision on mystery.
I think that's a beautiful place to pause in this room. Let's give one last round of applause.